Hi, my name is Olivia Hitchens.
And I'm Sean McLean.
And today we're going to be doing a tour of the ear.
First we'll start with the anatomy of the pinna. At the bottom we have the lobule. Then we have the tragus, the antitragus, and the intertragal notch. Along the side and the top is the helix, which ends at the crus of the helix. This bump right here is the antihelix, which divides into the crura of the antihelix, surrounding the fossa triangularis. Inside we have the cymba concha and the cavum concha. This divot right here is the scaphoid fossa. This entryway right here is the external auditory meatus.
Now review the physiology of the pinna. First, the pinna aids in the localization of sound. Second, the pinna enhances high-frequency sound, up to 3000 Hz. It's for this reason that those with microtia will have difficulty hearing.
Now that we've discussed the anatomy and the physiology of the pinna, we can focus our attention on the external auditory meatus, otherwise known as the external auditory canal. There's two main portions of the EAC, a lateral 1/3 cartilaginous portion and a medial 2/3 osseous portion. The inside of the canal is mostly epithelial tissue surrounded by temporal bone. Within it, there are sebaceous glands that create cerumen and hair. The EAC begins at the pinna and ends at the tympanic membrane.
Now we'll briefly discuss the physiology of the external auditory canal, or EAC. Within the EAC are sebaceous glands which create cerumen, as well as hair that help to maintain the cleanliness of the EAC. Also, the EAC helps to warm air before it reaches the tympanic membrane, so that the tympanic membrane can properly function. This is the tympanic membrane. Behind the tympanic membrane are three ossicles: the malleus, the incus, and the stapes. The malleus attaches to the tympanic membrane via the lateral process in the manubrium. The stapes attaches via the oval window. To simplify the middle ear, we may visualize it as a six-sided cube. Each face has several significant landmarks. The superior wall houses the tegmen tympani. The posterior wall contains the attidus, the pyramidal eminence, and the chorda tympani nerve. The anterior wall houses the tensor tympani muscle, the eustachian tube, the carotid artery, and the chorda tympani nerve. At the medial wall, we see the horizontal semicircular canal, the facial nerve canal, the oval window, the round window, the promontory, and a tympanic nerve. When looking at the inferior wall, we see the jugular fossa. And finally, the lateral wall, which isn't visible in this photo, contains the tympanic membrane.
Now we're going to discuss the physiology of the middle ear. What's important about the middle ear is that it acts as an impedance matching system. The three ossicles use lever action to save about 30 decibels of sound between the tympanic membrane and the oval window. This helps change acoustical energy into mechanical energy.
This is the inner ear. Behind the oval window is the vestibule, the cochlea, and the semicircular canals. Behind the stapes and oval window is the vestibule, the entrance to the cochlea.
Okay, so the physiology of the cochlea is a bit complicated, so we decided to break it down. I'm going to use this photo to help explain what happens inside the cochlea in terms of fluids, movement, and pressure. It's important to know that there are three main cavities within the cochlea: the scala vestibuli, the scala media, and the scala tympani. So the stapes presses against the oval window via lever action from the middle ear. That movement then creates pressure, and it pushes perilymph fluid through the scala vestibuli all around the base and up to the apex. Once that perilymph fluid reaches the apex, it then communicates with the perilymph fluid of the scala tympani via the helicotrema. Once that communication occurs, the perilymph fluid then moves down the scala tympani, down the apex, around to the base, and pressure is released through the round window. In between the scala vestibuli and the scala tympani is the scala media. This houses endolymph fluid and the organ of Corti.
If you were to cut the cochlea in half, you would be able to view the organ of Corti, the modiolus, and the spiral ganglia, which leads out to the vestibular cochlear nerve and the facial nerve. Now we'll discuss the physiology of the organ of Corti, which runs along the scala media. If you were to cut the cochlea, you would be able to view all three canals: the scala vestibuli, the scala media, and the scala tympani. Between the scala vestibuli and scala media is Reisner's membrane, and between the scala media and scala tympani is Basler's membrane. Perilymph and endolymph fluid stimulates both membranes, causing the outer hair cells to shear against the tectorial membrane, stimulating the inner hair cells, which sends a signal to the brain that a sound has been heard.
The vestibular system consists of three semicircular canals: the superior, horizontal, and posterior. Each semicircular canal has an end organ known as the cristae within the ampullae. The vestibular system uses fluids to help our bodies understand where we are in terms of space.
This aids in your posture, your balance, and your ocular reflex.
So just to do a quick review, we've gone over the outer ear, which consists of the pinna and the external auditory canal. The pinna aids in localizing sounds, especially high-frequency sounds up to 3000 Hz. The external auditory canal warms air before it reaches the tympanic membrane and helps keep the ear clean. The tympanic membrane is the end of the outer ear. It has three layers: the lateral epithelial layer, the middle fibrous layer, and the medial mucosal layer. Behind the tympanic membrane are the 6 walls of the middle ear and the 3 ossicles that are important for turning acoustical energy into mechanical energy. The inner ear then consists of the cochlea and the vestibular system. All parts work together to send signals to the brain that a sound has been heard.